Hello everyone. In this video, I am going to present the numerical validation of field static load test data of drill shaft. So at first, let me go through a background of this pile. So this is a pile load test taken from one of the projects in Bangladesh. So 23-meter pile has been prescribed underneath a treated water reservoir. So the whole structure will be underground, and that's why the pile cutoff level will be significantly lower than the existing ground level. The reduced level of the different different points have been provided in the screen, as you can see, and also the soil data has been shown. The pile length is of 23 meter, as I've already said. The pile diameter is of 900 millimeter, and the groundwater table, although not at the EGL, we are considering the pile. We are considering the groundwater table at the EGL. So we use this data and we calculate the pile capacity according to the AASHTO 2017 guidelines, and after that we make some springs, soil springs, so that we can use the soil springs in the software to numerically validate the data. So I will just jump to the Excel now. So this is the Excel file, and in this Excel file I have to provide the necessary inputs in the yellow boxes, as you can see, and after that it provides me the springs output. I mean the three different kinds of springs that we are providing. We are providing springs, lateral springs in the as the PY curves, and the guidelines are taken from the API, American Petroleum Institute, and we are providing TZ curves in each segment of the pile through the axial direction. So all the curves are generated in this Excel just from a calculation in the pile capacity. So this is the Excel, and what I did is that I have taken these values from this Excel and I have provided the input to the SAP2000 software. So I'll go to the SAP2000 software now. So I modeled this pile, as you can see. Let me show you a extrude view and a 3D view. So this is the pile. This is a circular pile, and we are providing load. We are providing a static load in the gravity direction at the top of the pile, and also we have provided the springs, as you can see. So each segment of the pile has three different types of springs. Two are in the PY directions to model the lateral capacity of the lateral resistance of the pile, lateral resistance of the soil, and in the axial direction the skin friction has been modeled. You can see the spring values. For example, this is the first segment, and in the U1 direction I have provided the TZ curve, and in the U2 and U3 direction I have provided the PY curves. All the PY curves won't be necessary in this analysis, but it is required to provide the stability. And in the end segment I have provided end bearing as a single spring. So end bearing provided, this is the end bearing spring, and only the values of the end bearing has been provided in the spring. So after that we provide a as we have already provided the load above, so I created three different load patterns. The vertical load, which is the first load, it will be provided three times, one in the loading direction, then again in the unloading direction, then again in the loading direction, and after that the load will be continued up to the 200% load that was prescribed in the pile load test, and after that again it will be unloaded to zero load. So we did this analysis and we did it like this. You can see in the load case though. So the first loading will be in the with scale factor 1, that means it will be just the load we have provided and in the vertical downward direction, and the loading 2 will be provided as a -1. That means the exact same load will be provided in the negative direction, I mean the opposite direction. So we can actually we can actually predict the unloading curve from that. And as you already noticed that during the soil spring definition, I provided multilinear plastic, and when you go inside you can see the hysteresis model and isotropic has been set. So I think if we do the unloading, in that case we will be able to find some permanent deformations in the soil. So we have run the analysis and the resulting data has been shown in the slide. So first I will go to this data. First of all, I'll go through some difference in AASHTO 2007 and AASHTO 2017. So AASHTO 2007 was previously used to calculate the pile capacity of the drill shaft, but in that case, in AASHTO 2007, the sand side friction was being calculated through a beta method that was dependent to the depth. It was not actually dependent on the SPDN values or the overburden pressure. But now in AASHTO 2017, only the sand and resistance method has been changed. The new beta method uses the SPDN values to calculate the sand and sand side friction. And after that, we can see that from the curve, the capacity of the segment increases by a lot. So overall, when sand layers are quite considerably high, in those cases the pile capacity in the AASHTO 2017 will provide a lot larger value than the AASHTO 2007. In the calculation of other things like clay side resistance, end bearing or sand end bearing, there is not any change between the two codes. This is the finding of the analysis. You can see the graph first. The black line shows the actual field load test data, and the red line shows the simulation that we have done in the software. You can see that it doesn't actually match the data very well. This might happen due to some reasons. One reason can be that the field data that we have taken was not actually from the same borehole that we are doing the pile load test. So as a result, as it is quite a distance far away, so there may be some deviations due to that. And other than that, if you we can see the data that it actually doesn't deflect very much away from the actual load test data. So we can say that the AASHTO 2017 method slightly overestimates from this analysis. We can say that the AASHTO 2007 slightly overestimates the stiffness of this sand layer. But we can see that after the first unloading, the permanent deformation that has occurred in the soil from the load test data and also from the analysis, we can find the same value. So we can say that the hysteresis type that we had selected, that isotropic hysteresis type, it can effectively portray the time dependent characteristics of the soil. And as from the previous slide, we had seen that the overall sand segments actually provide a more capacity in AASHTO 2017 than in AASHTO 2007. So we can say that when sand layers are considerably high, in those cases AASHTO 2017 can provide a much higher value of a pile axial load capacity than the AASHTO 2007. So these are the findings. This research is going on. We have planned to actually collect a lot of field load test data and simulate all of them, and in that way we can finally create some model to generate a value of the ultimate load capacity. Although you can see that in this analysis only we had gone to 200% of the load, we didn't actually go to the failure. So I think if we can create a model, and in that case we can finally predict the ultimate load capacity of the pile. So that's the objective. Thank you.